Hello? Hello? Hello, Karishma. Can you hear me? Hello?
Hello, uncle.
Hi,
Now I
Karishma.
can.
Sorry, I'm bit late because the last
Yeah,
it's
no problem. No problem.
back-to-back 3 sessions on Sunday after yours.
Oh, okay. Okay.
Okay, so we were discussing in the electricity, right?
Yes, yes, uncle.
Things like that. Can we continue
Yes,
that
yes.
one? Okay, so let me get the whiteboard and one second. Okay, where we ended last time?
Yes, uncle. So we saw that power is equal to VI.
Yeah.
Like,
So we derived
yeah.
that.
Yes, yes.
So you know the electrical energy and there is a power. Do you get that?
Yes,
We went
yes.
up to that point. And equivalent
Yeah.
in the mechanic side also, the
Mm.
gravitational side also, we did that. Let me first share the whiteboard and then start doing some. Okay, can you see the whiteboard?
Yes, uncle.
Okay. So now what we have come across, like there is something called the energy written always in terms of W, which is going to be the charge multiplied by the electric potential. Do you get that?
Yes, uncle.
Let me write that. This is our electric energy. And this is our electric charge. Electric charge. And this is our electric potential. Okay.
Yeah. Yes.
Electric potential. So this will look the same on the other side. W equal to mv. So this will be the gravitational energy.
Yeah.
Gravitational energy. And this is our mass.
Mass.
And this is our gravitational potential.
Gravitational
potential. Okay, so we should keep it quite handy, like potential. Either side, what is the understanding? Then what we did, the power is defined as the rate of work done with respect to time.
Yes.
So that came to d by dt of our QV.
Q into.
If the V is, we can take that outside. So it become a V times dq by dt. And we defined our, this whole thing is defined as our, this whole thing is our current I. So because of that, we got VI, right?
Yes.
Okay, good. So remember that everything got the unit. You start with the electric field, the unit is going to be volt per meter.
Okay.
Reason being, we have the definition later that helps to make this quantity as a better, easy way to write it as a volt per meter. I will come to that. Because the force, the electric force is going to be simply a Newton. That is the definition for the, derived for the, but the electric force, this Newton, we should be ready to write it in terms of a Coulomb volt per meter. Do you get that?
Okay.
Because the F is defined as the charge multiplied by the electric field.
Okay, yes.
Just multiplying the unit for the because the Newton, always it looks easy for the force, but we don't know the force is coming from the magnetic force or nuclear force or electric force or gravitational force.
Okay.
There are a lot of kind of forces. So immediately, depending on what force we are talking about, we should be ready to keep it in a handy way for the particular field, whatever the electric field or
Yeah.
whatever thing, as the other quantity. That will help us to do or calculate other quantity much easier. Do you get that?
Yes.
Okay. So now we define that the electric energy is going to be the F vector dot product with the displacement, right?
Yes. That's right.
Okay, so the S displacement could be our S vector. So this going to be, even though the unit is going to be our this side is going to be our joule straight away, but keep it handy to remember that it is going to be our Newton times our meter, which is going to be Newton can be substituted with the Coulomb volts divided by meter multiplied by meter cancel. So this will come
CV.
to our CV. This will be quite easy because this will tell straight away. This helps us. Okay, W electric energy can be calculated by charge multiplied by voltage. Do you see?
Yes, sir.
Straight away comes to picture. Do you get that?
Yeah. Yes.
So units always very handy. Okay, take it very powerful way to use it, to check the calculation and also to derive the formula or the equation what we require. And then the next one is the power, electric power, even though the unit we call that as a watts, but definition is dW by dt. So this side we are going to say that it is going to be the joule per second. Is that clear?
Yes.
But the joule itself we just calculated as a Coulomb volt per second.
Yeah.
So now we know that this can be written as a Coulomb per second multiplied by volt. Why we do that? This one simply is our ampere.
Okay.
So this will become a ampere volt. Okay. So this also immediately will tell power can be calculated by VI or IV, whatever it is.
Yes.
Yes. So that will come very handy also. So just to check the way the thought process and everything goes, can you tell me, we use in our daily life this one unit which is called kilowatt hour. Okay.
Yes, sir. Yeah.
Okay. So what quantity is this, and what is the meaning of this?
Power quantity.
Okay, you immediately say that this is a power quantity. I told you, we are meeting for so many days now, right? Have you checked the given quantity, everything in there, and then made this statement, or simply that whenever there is a watt, I will just say that it is a power? That is what you have done. You have done the second part. You have not put the thought process. Kilowatt is actually a watt, right? Because simply that 1,000 of them. That is the meaning. And hour is what? What is the unit? Which unit
second,
is
like
it's
time.
the second multiplied by second. Yeah. So you say that this watt multiplied by second is a power. That makes ridiculous, right?
No, yeah.
Do you see that? So don't quickly jump with instantly. That is what made the whole humankind not to develop their the brilliance or the intelligence as a overall average value is always low. Do you get that?
Okay.
We are ready to give up on what I see is true, or if somebody convince me, I will accept it. Do you get that? Why we should not do our analysis and take care of what we are doing? Do you get that?
Okay. Yes.
Okay. What you should have done? It is not simply a watt. It is a watt multiplied by second. How to deal with this? Now tell me. So this is completely wrong, right?
Yeah, it's not
wrong. Now, okay. Now I pointed out to you what mistake has happened. Now take care of it and tell me how to handle it.
Okay. We know this is what is,
yeah, that is what it is. Like I clearly went from the quantity, from everything, how to use the units, express that way.
Okay, so it will be, the watt is the unit for power. So be power into the time.
Yeah, but that is not going to help you. You need to use the unit in a different way. That is what I'm teaching you. Do you get that?
Oh, okay.
If you keep it again, what, or power, that is not going to help you.
Yeah.
What is the definition for the power and what kind of unit from the definition you get? Because time is a time. It is the basic, because there are 7 basic units that you cannot, unless otherwise you want to extract something out of it, that is not going to help you. Do you get that?
Okay, yes, sir.
Because they need to stay there to mingle with the other things, what is available as a derived quantity. So always keep it handy. The derived quantity can be always brought back to the level where we can get some sense out of that. That's the understanding, right? I'm saying
Yes.
that if I say energy, I told you, you don't know where the energy comes from. It could be because of the charges. It could be because of the movements. It could be because of the masses. It could be because of the particles in the nuclear, the subatomic particles. Do you get that?
Yes, sir.
So the energy or the force can be coming from all of these quantity or combination of these quantities. That is also possible.
Okay, yes, sir.
Because if you use a electrical energy to run a motor, it will be converted into mechanical energy. Do you get that?
Yes, sir.
So then we need to see, if you want to calculate the total efficiency of the whole system of how much electrical energy I input and how much mechanical energy I draw out, that will decide the efficiency of the system. Do you get that?
Yes, sir.
Then we should be ready to compare with all those things and how to calculate the efficiency. So those kind of system will become electromechanical kind of system. So we should be ready for that. But we are not even going to that point. We are still staying with only one particular system concept, which is only electricity. In the electricity, we learned what is energy, power, the electric field, the electric force, and we went to the units for all these things. But you find it a bit difficult to analyze when watts power is multiplied with the time, how to handle that.
So I'm not
The power, what is the power definition? You Karishma,
rate of doing.
Yeah, you cannot tell your mind in any way acceptance like I am not sure, I don't know. You need to step back to a level. Can I develop from a thing where I know something and then I can bring it out? Do you get that?
Okay. Yes, sir.
Giving up is easy. Do you get that? Okay. Don't expect the problem to be solved in an easy way. But our effort and the way we do has to be come from the clear understanding what we have. Can I build upon that? That is the way always it should be. Do you get that?
Yes, uncle.
So if I give you a simple problem like, okay, that there is a 1 volt applied across a 1 ohm, how much current flows?
1 ohm.
Yeah.
Unit will be 1 ampere.
1 ampere. You immediately do that. Okay. I would also do that, but I will take a step backward and make sure that even though it is a very straightforward plugging into a data into a formula like, okay, current is equal to voltage by resist V I equal to V by R. Put 1. Okay, answer is 1. You get that? 1 divided by 1 is a 1. But we need to make sure that what we are doing is right. When 1 volt is applied across here, 1 volt electrical potential is applied across here, a resistor which is giving a resistance for the flow of charges, which is 1 ohm, then the 1 coulomb flowing in 1 second, that is what is the amount of current we will get out. Do you get that?
Okay. Yes,
of that particular battery or through that particular resistor. That's the meaning. So 1 coulomb per 1 second is the 1 ampere. Do you see?
Yes.
Like that. So always we need to strengthen even simple problem solving. The analysis is very important. We need to bring up the analysis and make our understanding more clear, strengthen that, and also use it for doing problem in a confident way and in a correct way.
Yes.
So what is the problem in bringing the definition of the power?
We can write it as dW by dt.
Okay, dW by dt is okay. So that is the
Into-
rate of change of work done or energy with respect to time. What is the unit for dW? What is the unit for dt?
For dW, it's joules, and for dt is seconds.
Okay, so you are saying that this is nothing but joule per second multiplied by second.
Multiply by
Second
yeah.
cancel. What is the unit remaining?
Joules.
Okay,
So
joule
for-
is the unit for
Energy or work done.
energy. That's it. Not energy.
Yeah,
Second cancel. That's it. It's
Okay.
the energy. And we started with something coming from kilowatt hour. So most likely, okay, this is a wave, but this is an electrical energy. Do you get that?
Yes, sir.
Electric. So kilowatt hour is a electric energy.
Okay.
So this is what we call that as a 1 unit. In our electrical supply, power is supplied
Yes,
to our
yes.
domestic or industry. They don't care how intense you are using. Sometimes you may be switched on your refrigerator, your washing machine, aircon and everything. You may be consuming so much power. They don't care. They care about in 1 hour how much kilowatt you consume.
Okay.
So that, let's say if you have a one particular electrical component or a system like a microwave oven, which is running with a power of 1,000 watts, that means 1 kilowatt. If you use that microwave oven continuously for 1 hour, that will be, it has taken a electrical energy of 1 kilowatt hour. That is the meaning.
Okay, yes.
Then
sir.
we need to pay at a rate of 1 unit, whatever they charge in rupees, that
Okay.
amount, that is the exchange we are giving it for the electrical energy, not for the power. Do you get that?
Yes, sir.
Okay. So rather, like you could have consumed that 1 unit, like let's say there are 10 different appliances at home, and let's say they are all 1,000 watts. Okay.
Okay.
That means 1/10 of the hour is enough to consume 1 unit. Makes sense to you?
Yeah, yes, uncle. Yeah.
Okay, so that will be in 6 seconds. I mean 6 minutes.
Yeah.
Am I right?
Yeah, yes, sir.
60 minutes is 1 hour. 1/10 will be 6 minutes.
6 minutes. Yes, sir.
So take appliances like a aircon, washing machine, washing the dishwasher or whatever. All of them are nearly 1,000 watts. Do you get that?
Yes, uncle.
And if you take 10 of them, and if you switch on all of them and use it for 6 minutes, we have consumed 1 unit.
Okay. Yes.
Okay. So try to also derive the meaning out of these quantities and make sense out of that, so you can apply it, and so the solving the problem will be much easier if you do it that way. Is it okay?
Yes.
Okay. So now with this, let's do a bit of some circuits with what we have just done. So we have also looked into what is a battery. You're okay with that, right? So the battery is here with the electric potential V. You know how this is, and always the polarity is fixed for this. Is it okay?
Yes, sir.
Okay, so now let's say we connect it to a circuit. So the circuit, whatever it is, when the things are, we discuss about this, right? There are free electrons available in the conductor. Did we discuss about this or not? I don't think so, isn't it?
Yes, uncle. We saw this thing like
What will happen?
power is it?
No, it's not about the power. Don't jump. I'm asking about the basic understanding. What will happen if you connect a battery to a, let's say the circuit itself is a simple resistor.
Okay.
What actually is happening?
The flow of electrons.
Why the electrons has to flow?
Because of the charge.
The charge is always there. The whole universe is made up of charges.
Not charge, like because of the battery.
But the battery is
when switched on, it has a positive and negative charge. And
no, it is not a negative charge. Okay, the plate, yeah, okay, it is inside the battery. It has a potential difference because the charges inside the battery has been separated as a positive electrode and negative electrode. Okay, yeah, it got a charge of Q value. Okay, that is okay. But when you have a positive charge or a negative charge separated, what is that is going to do with the free electrons available to move around in the conductor?
The positive will attract the negative
Yeah,
electrons.
so the positive will attract the electrons because the electrons are free to move in the conductor, and the negative will repel them. So there will be a electron movement in this direction. Do you get that? We call that
Yes,
electronic
uncle.
current,
Yeah.
electronic current in this direction, but the conventional current is going to flow in this direction.
Yes, uncle.
Okay, so they are, as the voltage is time independent. So we are saying that this is constant. Mathematically, we say that dV by dt is equal to 0. That's understanding. Do you get that?
Yes, uncle.
So when this is constant, then the I will also be constant, meaning this is also constant. That is di by dt will be 0.
Yes, uncle.
Okay. So why we do that? Why we bring that analysis and understanding? Because what to be done, we can think about and do analysis using the mathematical modeling of this whole circuit or the system. Is that clear?
Yes, uncle. Yes, uncle.
Okay, so now we can do all sort of mathematical tool and concepts here. Let's start with the very simple one. Okay, let's change this the voltage battery as a variable one. What I mean is, it's not varying in time, but we have the choice to vary from some value to certain value. Do you get that?
Yes, uncle.
Let's say it is from 0 volt to 10 volt, for example. Okay.
Yes, sir.
That means what? You let's say start doing a experiment, and the experiment will go like that. Okay, so EC is to control the voltage. So the voltage. So remember that that is the same voltage available across the resistor also. Is it clear?
Yes, sir.
So that should be always remembered. It's not the battery voltage is the, even though there is a battery, in this case, the voltage across the resistor is exactly equivalent to that. Okay.
Yes, sir.
Because there is no way there is going to be any drop in the wire, because this is giving a friction for the flow of the charges. You get that?
Yes, sir.
Friction for the flow of the charges. Flow of the charges. Okay, I have received recently let me forward that to you. Okay, here memes which is really good. Okay, I will send it to you, forward it in the WhatsApp. Have a look.
Okay.
Did you receive it?
Yes, sir.
Did you get that?
Okay, yeah, the resistance and the current and the okay. Yes, sir. Potential.
Yeah,
Okay.
so the potential difference. Actually, they all three are connected. That is what we are trying to understand in a mathematical way and a physics way. But I'm just saying that thing, how to understand and everything, all the mass, whatever the concept we could make use of, it has to come into picture. Let's say the applied voltage, that is the voltage available across the resistor. So how we have to think about, we are having a variable battery potential, and we are going to use a ammeter which has a polarity, positive connected to here, negative connected here. And we have a resistor. Resistor, we use this symbol. Okay.
Yes, sir.
Okay. Then we are also connecting a voltmeter across the resistor. Do you get that?
Okay. Yes, sir.
Idea is, we want to, if R is the resistance value, this guy will calculate the current through the resistor. So we can say that this is going to be IR value calculation, and this is going to calculate the VR. You get that? Okay,
yes, sir.
Put the IR capital. The capital IR, and this is going to be our VR. Because why capital? Capital is for the constant values. If it is
Yes,
time
sir.
varying, we call that as a instantaneous. We use the lower case. Okay.
Okay.
If
Yes.
we are
sir.
saying that what is the VR measured in terms of volts, and this side, what is the current measure corresponding to that in terms of milliampere, for example. Is that okay?
Yes, sir.
Is to use the milliampere for because that is the thing. Let's say you apply 0 voltage, what you expect as a current? No current will flow.
No.
Let's say when you apply, for example, we do the 1, let's say we get 1 milliampere. Okay, let's
Okay.
take it as a 0.5 milliampere. So if
Okay.
it is a 2, we get 1 milliampere, 3, 1.5. So it goes 4, 2 milliampere. So we
Yes.
go up to 10 and we got, let's say, 1 milliampere. Is that okay? Sorry.
Okay.
No, it cannot be 1. 5
5.
milliampere.
Yeah.
5 milliampere. So humans are clever to devise some kind of instrumentation. We call that as the measuring instruments. And those those devices can be used in such a way the measurable quantity are done first. Do you get that?
Okay.
So if you think about it, it's not only the voltage and the current. Actually, it all started from electric field and the charges and everything. Measuring them is not easy. Do you get that?
Okay. Yes, sir.
So, but what is easily measurable is the voltage and the current. That is where we start our analysis and everything. Makes sense to you?
Yes, sir.
So by the look of it, whatever we measured, we varied our applied voltage across the resistor. That actually varies the current also. Do you get that? That is the first understanding. So immediately we provided something to the resistor and something, there is a flow of the current because of that. So the voltage caused that. So we write this as IR is a function of VR. Makes sense to you? So current is a function of, mathematical function of voltage.
Okay.
Why I write this? Because we learned f of x, right? In maths.
Yes.
If something is related to, so this is a dependent function. So when something is dependent, so this is our independent variable. Independent, remember that? Independent variable.
Yes, sir.
Variable, and f is a function, but it is our dependent on x. Do you got that? Dependent
Okay. Yes.
on x. So that's the beauty. So same thing, we are saying that in this case, so obviously when it is a f of x, then we would be drawing a graph between our x independent variable to the f value chosen, and the function will be drawn as a graph using these two axes, orthogonal axis or
Okay.
perpendicular
Yes.
axis. We get that? So we
Yes,
need
sir.
to do the same thing. In this case, this is going to be our VR in terms of volts, and this F is going to be our IR in terms of milliampere. Is that clear?
Yes, sir.
And we are having coordinate points 0, 0, 1, 0.5, like that they have. And if you start plugging in the dots, connecting them, it may look like this. Do you get that?
Okay. Yes, uncle.
Okay, all these points are, so we are going to have 10 different points. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 points. Okay. So we are going to connect these because it looks like a straight line. That makes sense also. So we are going to connect all these points with a straight line. Makes sense to you?
Yes, uncle.
Okay, that's the beauty. So you see, we started with a measurement, populating that and looking at the variation of what we applied is changing the other quantity. So then we use the mathematical knowledge that one is dependent on the other, and we know which is the independent variable and what is the other quantity dependent on that. Then we call the mathematical knowledge about a function and how to draw it as a graph, and what axis to be used as the independent variable and the dependent variable for reference, and then use the data points the coordinate points on that to draw the graph. Okay.
Yes, sir.
Then how to extend the mathematical knowledge when we see the graph? What is the name for this function?
Y
This
is equal.
graph is, yeah, it is a straight line. First of all,
Yeah.
this is a straight line. So that is coming to straight line. Okay. So that will immediately tell you y equal to mx plus c. That's okay. That is all the mathematical analysis are all fine. But by the look of it, as the voltage is increased, the current is increased.
Yes, sir.
If the voltage is decreased, the current is decreased. So straight away,
Yeah.
in an algebraic way, we can say that IR is proportional to VR.
Mm.
You get that? Then
Yes, sir.
a proportionality can be made it as an equation by introducing a constant
A
of
constant.
proportionality multiplied by the other quantity. Now, how to understand what is this K? Write the K in an algebraic way. That will be IR
V.
divided by VR.
Yes, sir.
You get that? So unit will be
Yes.
powerful one which can help us to understand very easily. So current unit is an ampere. The voltage unit is a volts. You get
Volt.
it? Okay.
Yes, sir.
Ampere
Yeah.
per volt. So ampere per volt, look at the circuit. We have used the battery which got the voltage. Okay. And the
Yes, sir.
current is the ampere which is flowing. So those two ratio, so that is actually telling us there is another component in the circuit which is going to influence the ratio between these two. That is what the proportionality means. Do you get that?
Yes, sir.
So now, we could have defined the ampere per volt as our unit for this R, which is the circuit element, but we defined the unit for the resistor as a ohm, which is defined as other way around. That is a volt per ampere.
Yes, sir.
Okay. So when you compare this with our K is actually defined as our ampere per volt. So this is going to be reciprocal. Do you get that?
Yes, sir.
Reciprocal. That tells us K is nothing but 1 over R. Is it clear?
Yes, sir.
So that gives a, only through algebra, we derived the IR must be equal to 1 over R multiplied by the VR. Is it clear?
Okay, yes. Yes, sir.
Okay, so this is through the algebra. Okay, fine. So now, how to do this straight line? From the tabular column, the points are put it into the graph, and mathematically we understand y equal to mx plus c is our straight line equation. Now look, try to solve it or analyze it graphically. We know that this is 0 because the intercept is
Yeah.
point is 0.
Origin. Yeah.
Origin, that means c is 0. And name all these quantity. X is our VR.
Yes.
And M is going to be the change happened in the Y divided by the change happened in the X.
X. Okay.
Okay. So this will be equal to, the Y is actually okay, I should not put the equal to Y, I put the equal to, I don't know. This quantity is our IR. Do you get that?
Yes, sir. Yes, sir.
So delta Y is also written as in our case, delta IR, and delta X is written as a delta VR.
VR.
This
Yeah.
whole thing, equation now simplifies to IR. This is a graphical way of making the same mathematical model. So this will be our delta IR divided by delta VR
VR.
multiplied by VR.
VR.
VR. Is it clear? So
Yes,
what is
sir.
our M? So you take any 2 points. Okay, so we can take these 2 points. For example, this is 0, 1, 2. So this will be, when you apply 2 volt, the current is going to be 1 milliampere. Is it clear? 2, 3, 4, 5. So this is going to be, when you apply 5 volt, you are going to get a 2.5 milliampere. Is it okay? Hello?
Can you hear me, uncle?
Yeah, now I can hear you. Can you?
Okay, yes, yes. I told you. Yes, sir.
Yeah, okay. Now only I can hear you. So you get the
Okay.
coordinate points, right? This
Yes,
point
sir.
is our 1, 2, and this point is our 5, 2.5. As it is a straight line, any 2 points is okay because no change is the change is independent of the when you move along the line, the change happening with the coordinate points will be independent of the both the x or the y. You see that,
Yes,
right?
sir.
What we mean, if you calculate the delta IR, this will be our 2.5 minus 2 will be a 0.5. You get that?
Yes, sir.
What I made somewhere some mistake. What is that? Now 1, 2 and 5, yeah, that is okay. Yeah, this is going to be 0.5, right?
Mm.
Okay, so this is going to be our delta VR is going to be our 3. Something fishy for me. No, it should be 2, yeah. Now I know where the mistake is. Coordinate point is not correct.
Oh, it's 2,1.
Yeah. So
Okay.
that made things fishy. Okay. So this is going to be 2, 1. So that makes this is 1.5, right?
Yeah.
So the 1.5 and 3 volt difference gives you change in the current as 1.5 ampere. Yeah, that makes sense. 1.5 ampere. And this delta VR is going to be our 3 volt.
Yes.
Okay. So with this, we can calculate M is nothing but our the delta IR divided by delta VR is going to be 1.5 divided by 3, which is going to be 1/2 is okay.
Yes, sir.
1/2. And we know that the unit of the M is also going to be ampere per volt.
Yes.
Okay, so that tells us this is our straight away our K itself. Do you understand that?
Yes, sir.
And we know that K is actually equal to 1 over R. That is going to help us to calculate the R is 1 over M, which is going to be 2 over 1. And we have to be careful with the unit because it is a volt per milliampere. Is that okay?
Yes, sir.
Okay, so that will be 2 multiplied by 10 power 3. So this is going to be 2 kilo ohm. Okay, so we calculated that this guy is 2 kilo ohm. Is that okay?
Yes, sir.
Okay. You see the analysis and everything. We went from
Yeah. Yes, sir.
measurement, put it in a tabular column, use algebra to analyze and get the
Yeah.
mathematical model. Same mathematical model can be obtained using the graphical way from the understanding of the straight line and the equation of the straight line. And we continue further for the next one, which is the more powerful and universal one. We have the data points which looked like B with IRVR in terms of the volt and so 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And this value are 0, 0.5, 1, 1.5, 2, 2.5, 3, 3.5, 4, 4.5, 5. Okay. So I write all of those values. Why I do that? We normally do the experiment conveniently this way because when you find the delta VR, which will be in terms of volts, the difference will be always a constant value. This makes
Yes,
our calculation analysis easy. So we get the 1111 for all this value. And as this is changing, we need to find the delta IR also, which will be in terms of milliampere. So this is a milliampere and this is our volts. So this is going to be 0.5, 0.5, 0.5, 0.5. Do you get that?
Yeah, yes, uncle.
Okay. So as I said, when the VR changed, the IR changed. So we call this as the IR is a function of VR. Do you get that?
Yes, sir. Yes, sir.
So whenever we have a function, so the mathematics says whenever we have a function dependent on an independent variable, then we need to know how it varies. So graphically we did it, and algebraic also we did it. More powerful one is we need to be interested in what is the change happening to the function for a small change happening to our independent variable. Do you see that?
Yes, sir.
Because x is saying I am changing from x to x plus dx, and f may be changing from f to f plus df. So we are interested in the ratio of the change happened to the function for the corresponding change in the independent variable. Do you get that?
Yes, sir.
So that will give us the better idea. So what we do the same thing. So this is the 0.5, 0.5. Here, this is a function. And now you see all of these are all constant. Do you get that?
Yes, sir.
But the constant has to be done in a better way. So not only the difference in the IR itself. So the delta IR divided by delta VR. Okay, so this is the one we are interested in. This will be volt,
Yeah.
milliampere per volt.
Per volt, yeah.
Okay, so this will be 0.5, 0.5, 0.5. Okay, so now these quantities are all constant.
Yes.
Okay, so we define this quantity as our K also, which is our 1 over R. That makes sense because why this is a constant? If you further differentiate the K with our dVR, this will be 0.
Yeah, yes, sir.
K by D, okay, not K, R. dr by dr will be a 0. You get that? That is what the meaning
Yes.
of the constant. So these quantity, both are constant. So constant. So that will be popped up even in our equation also what we derive. We derived I is going to be 1 over R multiplied by V. Is it clear?
Yes,
If
yes.
you find di by dt calculus wise, you will get an answer 1 over R. And if you go for d square I by dv square, it will be 0.
Yes.
This means our R is a constant.
Okay.
So this is how the analysis. So in mechanics, we did that, right? We derived the V equal to the first differentiation, second differentiation.
Yeah, yes, sir. Yeah.
All these things, the same analysis. So we should be ready to use our all the mathematical skills and the knowledge in the different concept to be ready to be applied and used. Is it okay?
Yes, sir.
Okay. Any questions so far?
No, no questions.
You are okay with that. Okay, let's go to the next page. Okay, so now we have some understanding about, so straight away now we are very powerful. So because we have a mathematical model for a resistor straight away, for a DC, a fixed voltage value means as long as the R is a constant, then the current is going to be a constant. And we have that is what the Ohm's law says. At constant temperature, the current flowing through a circuit should be directly proportional to the voltage. This is what the Ohm's law is. Okay.
Yeah, yes, sir.
Ohm's law, and from there we derived the I is nothing but 1 over R times our V.
Yeah.
Okay. So to take it further, what is really this is doing? Tell me what the resistor is doing. Physically, what it does.
It's resisting the current flow.
Yeah, that is
like,
put it in a more sensible way. It is resisting the current, but what it is really
decreasing.
No,
no,
decrease or something. No, the current will be constant. You don't resisting means not reduction. Do you get that?
Yeah.
Actually,
Right.
that is the one deciding how much current it has to flow. Do you get that?
Okay, yes. Yeah, okay.
It gives friction for the flow of the charges. Don't
Okay, okay.
forget that.
Okay.
Friction.
Okay. Yeah, yes, sir. Yeah, friction.
So what the friction will do? There will be loss of energy. Do you get that?
Yes, sir.
Consequence is loss of energy. Loss of energy. So we don't go directly for the energy because we are more in terms of voltage and current. We go for the rate at which the loss of energy. So we go for the rate. So that is the power. Okay.
Yes, sir. Okay.
Power. So there will be heat energy. So this will be dissipating heat to the surroundings. So there will be heat. Heat. So there is a power dissipated. So heat, power dissipated. Power dissipated to the surroundings. Do you get that?
Yes, sir.
To the surroundings. So now we need to calculate that power. Power, we know electrical power can be calculated by VI. So now we include this Ohm's law in there. So this can be written as, instead of I, we can plug in the 1 over R times V. So we are bringing in this here. So this gives you V square over R as a one equation. If you use only one instrument to find only the voltage across the resistor, then we can just square it divided by the R value will give you how much is the heat power loss. Is that okay?
Yes, uncle.
And the power can be also calculated VI. This time change the subject to V equal to IR. Then if you plug in this one to our, this will become IR multiplied by I. So this will become I square R. So if you know the
Yes,
current, you can directly square it and multiply it with the R will give you the answer straight away. Is that okay?
Yes, uncle.
Okay. So this is, even though we say that heat dissipated and everything, this is what the power is consumed by all the appliances. So as I told in the beginning, like 1000 watts is used by the microwave oven. So it is going to convert the electrical energy into microwaves, and the microwaves are the one which is going to heat up the food and everything. You get that?
Yes, uncle.
So that is what the power consumed per second will be. So the total time and the power multiplication will give you the energy consumed by every appliance. Is it okay?
Yeah. Yes, uncle.
Okay. So now let's get into a bit more practical situation. So we call that, okay, there is a battery. And then when you put a resistor, we say that there is a voltage available as a positive, negative. Conventional current flows from here and flows here, comes out here, same value, decided by the R, that will decide the I value, as I is actually equal to V over R. Fine, all good. Now they come to I. When they come to the negative side of the battery, polarity of the battery, what will happen to the charges?
They will repel kind of, right?
No, this is a conventional current direction. You are talking about the electron. So the conventional current getting into the negative side of the battery is same as the electronic current which is repelled by the negative side of the battery. Do you get that?
Okay.
You are confusing with this too. So we are saying that
Okay.
there is a electron flowing in this direction, which we always draw it as a conventional current direction flowing from positive to negative.
Okay. Yes, uncle.
So even if you think from the electron point of view, okay, the negative side has repelled the electron, positive side has attracted the electron. What will happen?
Yeah, it works.
When it get attracted by the positive side of the battery and the electron from the negative side is getting repelled, what is happening at the battery? Don't you think that the same electron which is attracted by the positive side of the battery has to flow through the battery? That is what is coming out as the electron continuously to keep the current same value.
Yes.
Don't you think that?
Yes. Yes.
So the current is flowing through the battery also. Do you get that?
Yes, sir.
There is no question about that. Otherwise, it won't continuously give
Yeah.
you the electrical energy for the circuit to operate. Makes
Yes,
sense
sir.
to you?
Yes, sir.
So we are saying that the battery is actually made with all the negative charges separated by the tank and a positive electrode put up here. Now, because of the current flow, so we connected a resistor with this. Do you get that? This is what we have
Yes,
done.
sir.
This is negative polarity. So the current is flowing. So through the R, I is flowing. I is getting in conventional current. So the the positive charges are sitting here.
Yes, sir.
Okay, so the amount of charge is not going to reduce as long as the V is the constant. Because the positive to negative, there will be a electric field. You get that?
Yes, sir.
So all these electric field combined together and how much is the charge value is separated and the distance between them, the D distance between them, they all decide. The voltage of the battery is nothing but the E multiplied by D. Is it okay?
Yes, sir.
Okay. So now what we are doing, completing the circuit, we are making the current to flow. So we are saying that there is going to be a current flow. You get that? I
Yes,
is
sir.
flowing here. So when they are flowing through this solution or whatever the emulsion or the aerosol or whatever it is, they are going to have some amount of friction here also. Do you get that? Depending
Yes,
on the
sir.
material and the way we designed and everything. So this will have some friction. And we call that as the internal resistance of the battery. Internal resistance of the battery. Is that okay?
Yes, sir.
So that will have its own resistor. So ideally, we draw this circuit in an ideal way, but in reality, we need to say that this is an ideal battery with potential V. In series to that, there will be a internal resistance of a battery. Do you get that? This is what is our whole batteries. Make sense to you?
Yes, sir.
And this is connected to our resistor. So the circuit is not straightforwardly this V equal to IR is going to work now because the I flowing through this R coming out here, that same I flowing through this is going through this ideal battery also. Do you get that?
Yes, sir.
But now think about it. When the I current flow through this RB, it will follow its own Ohm's law. Do you get that?
Yes.
There will be a VRB potential. So this VRB potential according to the Ohm's law will be IRB. Makes
Okay.
sense to you? And
Yeah, yes, sir.
similarly, there is going to be a potential across our this VR. So the VR is going to be our IR.
Okay.
So now we have some extra mathematical analysis to be done, how to go about calculating the current. This cannot follow this simple equation. Do you get that?
Yes, sir.
Okay. So for that, we need to learn two more Kirchhoff's current law and Kirchhoff's voltage law.
Okay.
Okay. So we will look into that next week. Is it okay?
Okay. Yes, sir.
Okay then.
Okay.
Okay. Take care. Yeah.
Okay. Thank you, uncle.
Yeah. Bye.